Hey guys, today I'm going to be talking about chemical kinetics, something that you will undoubtedly see on your AP exam and something that you will encounter in next year chemistry or later on in like college chemistry, something like that. So first, what is chemical kinetics? I define chemical kinetics simply as the study of rates. And what I mean by that is if you have a reaction and you want to know how changing the concentration of the reactant affects the speed of the reaction and the rate at which the reactants and the products are increasing or decreasing in concentration, then you use kinetics. So just very quickly, I'm going to go over the three kind of orders that we have. And it'll probably be, before I do that, it'll probably be simpler to just introduce this equation at the bottom. This is our basic rate equation. Rate equals concentration of A to the X times concentration of B to the Y. And then there is a rate constant out in front. And this rate constant can be determined experimentally as well, or if you have experimental data, then you can determine it mathematically. And then the X and the Y on the A and the B has nothing to do with the coefficient out in front of the A and the B in the equation or anything like that. It has to be determined experimentally. So first, zero order. What zero order means is that if you change the concentration of a certain reactant, then if you change the concentration of a certain reactant, then it's not going to affect the rate. The reaction will proceed at the exact same rate with the exact same changes in concentrations of reactants and products. First order means that if you change a concentration of a reactant, the change in the rate is going to be directly proportional to that change in the concentration. So if you double the concentration of a reactant and the rate doubles, then that's a pretty good indication that it's first order. And then second order is means that it's gonna be directly, if you change the concentration of A, like let's say you double A, then the rate of the reaction is going to increase by 4 times what it was. Or if you triple it, then it'll increase by 9 times what it was, so on and so forth. So basically, the change in your concentration is creating an even larger change in your rate. So we're going to examine, because the two things that I can almost guarantee you'll have to do on your AP test is determine the order of certain certain reactants in an equation, in a reaction. You're going to have to determine it mathematically, and you're going to have to determine it graphically. So first, we're going to look at how to determine the order of reactants mathematically. So here we have just a sample reaction that I put up here. It's permanganate reacting with chlorate and hydrogen ions to form manganese ions, perchlorate, and some water. So here you can see when you're determining it experimentally, you need to have multiple trials, and the reason for that will become evident as we go through this. So let's say you have, so in this I'm going to put all 3 of my reactants, the permanganate, the chlorate, and the hydrogen ions, and then to determine it, and then the rates over here. So then to determine the order of each of our reactants, we're just going to examine how changing the concentration of our reactants, our initial concentrations, how that affects the rate of the reaction. So obviously my rates here are pretty simple. You probably won't see things like numbers as simple as that, but the methodology here will stay the same. So first let's look at the permanganate. As you can see, between trials 1 and 2, the concentration of permanganate doubles, while the concentrations of chlorate and hydrogen ions stay exactly the same. So between these two, the concentration is 0.2 to 0.1. So obviously you can see that's a twofold increase in concentration, while the rate is 8/2 is a fourfold increase in concentration. So what you can see here is that so if you wanted to determine it, if mathematically from there, if there weren't numbers as easy as 2 and 4, you would just take the ratio that we got with our concentrations to the p power equals the ratio and the rates, and then you solve for p. Right here we can just see in our heads that p equals 2. So that's telling us right now that the permanganate is second order because we double the concentration and our rate increase by fourfold. So then for the chlorate, we have trial 3 is where the concentration for chlorate changes. So if we compare trials 1 and 3, where everything else is the same except the chlorate ions, then we'll see that it's a 0.30 to 0.10, so 3, and the change of the rate is 6/2, which is 3. And right here, because these match up, you know that it is first order. And then for the hydrogen ions, you have the change occurs in the fourth trial. So if you come in the first and fourth trials, you'll get a twofold increase in the hydrogen ions and a twofold increase in the rate. So 2 to 1, 4 to 2. So that's going to be a pretty good indication that this is first power. So we have second, first, first. So our rate law for this would be rate equals K times the concentration of permanganate, I'll put minus right there, times concentration of chlorate, times concentration of hydrogen ions, and make sure to note that the perchlorate is taken to the second power because it is second order. That's how you determine it experimentally from reported rates. Next we're going to go over how to cover it graphically. Doing it graphically will probably come up on the AP test. They'll probably show you graphs and you'll have to determine it that way. But you're also going to have to do it for labs next year. So if you forget this, you can come back and watch this video next year in order to jog your memory on how to do the kinetics lab. So for what you're going to do for here is, so when you're determining it graphically, basically what you want to do is it all goes back to these equations that I put up here at the very beginning. All these equations are called integrated rate laws. And if you look at the form of them, they're all in a linear format. So they're all y equals mx plus b, but with different, but with k as your m, t as your x, and then the concentration as your y. So, and then of course, the concentration at initial is going to be your y-intercept. So you can think of that as your b. So, so what we have here is when you're comparing when you're doing it graphically, you simply want to compare for zero order, you just do concentration of A versus time. For first order, you do the natural log of the concentration of A versus time. And for second order, you do 1 over the concentration of A versus time. And if you have the data from an experiment, how the concentration of a reactant changes over time, then you can just graph these three things and see which one is the most linear graph, and that'll be your that'll indicate what order A is. Now, one thing that we ran into when we did this lab is a lot of times, depending on how accurate your data is, you can't really see that much of a difference between the 0 first and second order graphs because it isn't that evident to the human eye. In which case, I would recommend that you can go, if you're doing it on a computer, which you will be for your labs, just plot a line of best fit and look at the R squared values for those, and whichever one is higher is the most linear one, and that'll indicate what order your reactant is. So the last thing I want to talk about is pseudo first order rate laws. And this will also come in handy later during senior year, and I'm sure during higher levels of chemistry. And what that is, so let's say you have your rate equals K times A to the X, B to the Y. So here, as you can see, we have a lot of variables that, depending on how the experiment is set up, we might not know. So in order to make it simpler, basically what you can do is, even though this obviously isn't first order because you have two different reactants, you can make it a pseudo first order rate law by basically eliminating the second one. And how you do that is you experimentally you create a large excess of one of your reactants. So you have a large excess of this. So let's say your concentration of A is 0.001 molar. All right, and let's say you have 10 milliliters of that. Then your concentration of B is 100 molar, which I mean is unrealistic dealing with most things, but just for the sake of this, we'll say it's 100 molar, and let's say you have 10 milliliters of that. Well, obviously this is in huge excess, and it's going to use very, very little. So you're probably going to have like 9.99 something milliliters of this left, while all of this reacts away. So because the change in this was so small, we can basically get rid of that whole term. And what the rate law becomes after that is K prime of AX. And basically K prime here equals K times B to the Y. So you can solve for X first, the order of one of your reactants. You can use that to solve for K prime. And then you can use K prime to solve for either Y or K. So that's basically what you need to know for chemical kinetics for the AP test and for senior year and higher level chemistry. I hope this helped you out. If you have any suggestions or comments, either leave it below the video or send us an email. Thank you.